Hey, Sec 2 there, students. In this video, we're going to do the week 7 Muddy Points, which is just focused on correlation. So let's just jump right into that. So the first thing that came up was the correlation coefficient calculations. Pearson correlation, calculations. One of the muddest things was the correlation question. Using formulas is probably the muddest thing for me at this point. I'm still having trouble understanding the new formula. So the thing that I would point you to is one is that when we're doing the calculations, this is the one that I would suggest that you focus on. Use the computational formula. The definitional formula, while it's nice and it's meaningful because you kind of see what you're doing throughout it, you run into problems when you don't have easy means, so means that are fractions. So if you have means that are fractions, it ends up being a nightmare. This is the one to just get used to using. So you're going to essentially create this table. So you're going to be given this data here, but then you're going to want to have sum of x, sum of y, sum of x squared, sum of y squared, sum of x times y. All that gets plugged into three formulas: sum of squares x, sum of squares y, and sum of products. And then once you've got those three components, that gets plugged into your correlation coefficient. So less calculation, but that's where I would, again, just focus just on doing the the computational formula. The other thing that I want to suggest is that in our on Canvas, there's the hypothesis test calculation video for correlation. There's always one hypothesis test calculation video for all of the test statistics. Watch the one on the correlation. Again, it will just walk you through using the computational formula, walk you through using the steps. And then the solutions in WebAssign should be super helpful as well. So that's kind of where I sort of point you to regarding the correlation calculations. As for this next one, the thing that tripped me up most this week was the R critical and how we reject or retain the null. I'm so used to using p less than 0.05 being significant and p greater than 0.05 being retained that I have to be careful, because that's not how our R critical works. If we exceed our threshold with our R values, then it becomes rejected. And if it's under the threshold, then we retain the null. I'll have to be careful with that going forward. And then also the fact that degrees of freedom is n-2. Okay, so nothing is different actually. All the test statistics we've covered, all of them that we will cover. If you end up with a p less than 0.05, it is statistically significant, or depending on your alpha. But let's assume we're using an alpha 0.05. Then p less than 0.05 is significant, statistically significant, and p greater than 0.05 is not. So if we find a statistically significant result, we are rejecting the null. If we find a non-significant result, we are retaining the null. That has not changed at all. I'm not sure where this person's getting this from, but basically all along, because maybe what they're referring to is that when we get to they were going over the R, is, you calculate this R, and if we walk through the steps here, we set this critical region, and then we see where our R is, and we compare it to the critical region. Well, we've been doing that all along. Every statistic, the z-score, the t-tests, and the ANOVA, we calculate the test statistic, and then we see, where does that fall? Does it fall into the critical region? So if it falls in the critical region and we're using an alpha 0.05, then it is p less than 0.05. But if it doesn't fall in the critical region, then it is p greater than 0.05. So nothing's changed. So I'm not sure where that individual, how they were doing it. It's a good chance is that they may have been using statistical programs to do some of the calculations for them, and then they're just looking at the p-value to see, is it less than 0.05, and then they know it's statistically significant, and if it's not, then they know it's not significant. That's how you do it if you're using the program to do all the calculations for you. But what I've been teaching you is how to calculate the test statistic itself. Once you've done that, then you're seeing, is it an extreme F ratio? Is it an extreme, in this case, correlation coefficient? And if so, then that's where we start to question the null, and we're ultimately going to reject the null. So to finish up on this idea of the statistical decision making changing, nothing's changed. It all just depends on whether you're doing it where you do the calculation of the test statistic, use the tables to determine a critical region cutoff, and determine if that test statistic that you calculated crosses the critical value and puts it into the critical region. If so, reject the null, p less than 0.05. If it doesn't cross the line, retain the null, p greater than 0.05. However, if you're doing it with statistical program, then you can just look right to the p-value because it will tell you the exact p-value for the specific test statistic. Okay, the next one here is effect size. And so one of the things that I would say in terms of the effect size, I'm having a bit of trouble understanding how to interpret the effect size. Again, just in general, an effect size tells you what is the impact of the treatment that you gave in the research study, or if you had different conditions and you were comparing different groups, what was the impact of the differences, a control group versus an experimental group, or visualization instructions versus pronunciation instructions. What was the impact? That's what the effect size measures, is how much. So it's essentially how big is the impact, the size of the effect. The statistical significance just simply tells us whether the result we got was likely to be due to chance or not. So essentially, you want to ideally think about when you interpret and look at a empirical research study, you want to look for two things before you start to think a treatment is worth administering to one of your clients or a patient. And that is, one, it should be statistically significant. That means that in this research study, we're thinking the impact was not by chance, because it's possible that you take a group of people and you do something to them and they get better, having nothing to do with the treatment. It is possible that that just simply happened by chance, usually due to some form of sampling error. But we want that to be a very low likelihood. So that's what statistical significance tells us. The result we got, unlikely to be just due to chance, due to sampling error. So as a result, we're going to bet on there being a treatment effect or a difference based on the conditions. Now, once we've got established that, then we want to look at, well, how big is the impact, or how big is the difference? Because again, if I'm a clinician or working with people and I want to implement this treatment or these different experiences, conditions, part of what I want to know is will it have much of an impact? That's what the effect size measures. Is it tells you, will this pain medication have much of an impact? Will the person really get that much reduction in their pain? And so that's what the effect size measures. Now, when it comes to a correlation, effect size is just looking at, because in a correlation, what we're simply saying is two variables that we've measured are related to each other, or in other words, they correlate. If they're related, the effect size is measuring essentially how much are they related. So statistical significance is, again, one thing. We can get a correlation, and we want to know, is this correlation likely to be happening by chance, or is it more likely to be happening because there actually is some kind of relationship? So that's always our first step, is that we want to establish statistical significance. Just simply means that once we measure these two variables and we saw that they're related, that relationship is not likely to be due to chance. Still could be, but unlikely. So low likelihood or low probability, we're going to bet on there being a relationship. Then next step, effect size. How big is the relationship, or how strongly, not so much strongly as how much do these two variables overlap? How much of their relationship is like connected to each other? So one of the ways I think that can be helpful to look at this is, let me shift to this, is if we look at a correlation. So what we've got here is a correlation between two variables. Right now, this correlation is a correlation of 0. Now, if I drag this, and I'll make it a better correlation. So now I've got a correlation of 0.70, right? So what you can see is that if people tend to score lower on X, they tend to also score lower on Y. If they tend to score in the middle on X, they tend to score in the middle on Y. If they tend to score higher on X, they tend to score higher on Y. Okay, so we've established there's a correlation. The correlation is 0.70. Now, let's say it ends up, because we have enough participants here and so on, we run it through our statistic, we calculate the correlation coefficient, and it's in the critical region. What that's telling us is that the x and the y variable are likely to be related to each other, that it is unlikely that what we're seeing here is just by chance. Because it's possible. We have, how many people do we have here? I forget what my n is. I don't think I have an ability to do that. But it looks like we're talking maybe 40, 50 people. No, maybe less than that, maybe 30 people. And so we've got 30 people here. Well, are these two variables truly related, or does it just happen to be the 30 people we happen to select have a correlation of 0.70, right? So that's statistical significance. So let's say we've established that it is statistically significant. So we've got this correlation of 0.70. Now what we want to look at is, well, how big is the relationship? How strongly are these two related to each other? And that's where you square the correlation. So 0.7 squared is 0.49. What that tells us is that there's 49% shared variance. And that's what you're seeing in this Venn diagram here. So think of this dark blue as variable x, the light blue as variable y. So essentially what you can see is that, and if we just focus on one of them, so let's say I wanted to know what percent of the variability in in y. So these highs, so again, you get high scores on y, middle scores on y, low scores on y. So we're just looking on that y-axis. Think of that as all the variability. Some are high, some are low. That's in this light blue circle. Notice that a good chunk, almost basically about half of that entire light blue circle, is shaded dark blue or black right here. And that's because it's sharing the variance with the x variable. So what we now know is that what percent of the variability in y can be explained by knowing somebody's score on x? About 49%. Okay, so that's a very strong effect. It is a large effect size. And so remember, what we're calculating here is our r squared. And r squared just simply is telling us the size of the effect. And so again, we have small, medium, and large. And in terms of small, medium, and large effects, it's the same as it's always been for an r squared. 0.01 is a small, 0.09 is a medium, and 0.25 is a large. So the fact that we have this 0.49 or 49%, that's a very large effect. So these are strongly related to each other. That's essentially what the effect size measures for us. All right, next one. Correlation versus causation. So this is an important one, because when we're doing a correlation, all we are simply doing is measuring two variables, running them through a correlation coefficient to see if they are related to each other, if they correlate. So what does that mean? That means it's like, do they seem to vary together? Like, do they seem to be connected or related to each other in some way? So once we have established that there is a correlation, so anything that's not zero or around zero, correlation of zero says these two variables are not related to each other. But anything that's beyond the zero, like, so again, you get higher number, whether it's positive or negative, you're getting more and more of a relationship, all the way to +1 and -1. Those are perfect relationships. So correlation coefficient just says, hey, there's a relationship. The question then becomes, why is there a relationship? And we don't know. All we did was measure these two variables, run them through a correlation coefficient, and they seem to be related. And again, ideally, we look at a statistical significance, and we find that it is statistically significant, so it's not likely to be happening by chance. And then it also shows us that there's a reasonably large effect size, right? So once we've established that, that's all we really know. And what we don't know, which is what your brain is always going to want to go to, is why are they related? And this is where we have to be super careful, and we don't want to get caught up in going to a causal explanation. Okay, so when we get to interpreting correlations here, one of the examples that I use in the slides is this one here. So here, if we looked at this data here, it's a very strong positive correlation. I'm guessing that this correlation is around a 0.8, 0.9, somewhere in there. So it's a very strong positive correlation. Let's say it's statistically significant and it would have a large effect size, because it's going to be like, if it's a 0.8 at worst, it's going to have a R squared of 0.64. So 64% of the variability in how many crimes are committed is related to the number of churches in the town. Okay, so at this point, we've got these 10 cities. The number of churches they have in those cities and the number of crimes that are committed in those cities are strongly correlated, unlikely to be due to chance, right? Okay, so then at that point, why are these two variables, number of churches and serious crimes, related? We don't know. There are multiple explanations. That's the whole point of correlation does not mean causation, mainly because people want to go to cause. So your brain is programmed to want to explain things causally. It just is. It's how we live through life. So again, something happens in our lives, and if I hit myself in the head and I'm like, ow, my head hurts, and then I hit myself again, it's like, ow, my head hurts. Eventually, we need to, as in order to survive, realize, hey, hitting yourself in the head is what's making your head hurt. Stop hitting yourself in the head. So our brain's always looking for causal things, so then it can avoid things that create problems for us. So no, your brain's going to do that. And so what a lot of brains are going to want to see is that, oh, well, that's weird. These two things are strongly related. It must be that churches are causing crime. Now that one seems kind of silly. And so thankfully, a lot of people's brains aren't going to go to that. But that is not unusual for people to do that, that's where they're going to go with this, is they then, again, two things are correlated. They then want to say it's a causal thing. Because I could also have replaced churches and crimes with amount of hours spent studying and grades in a class. And, let's say we got a strong positive correlation here. Most of you then, I would probably argue all of you, will then say, well, if I asked you what should you do to do better in his class, everyone would say study more. Because it's logical, it's rational. But that's not what our correlation tells us. All our correlation tells us is that they're related. We don't know why. And we have to be okay with that. We have to be comfortable in the ambiguity, in the not knowing. And the reason why is because there are multiple explanations for any kind of relationship. So let's just go through the churches and crime one. So one is we call the directionality problem. It is certainly possible, I'm going to keep advancing it here. It is certainly possible that churches are causing crime. I mean, it seems silly rationally or reasonably, but maybe it's a great place to get together and meet other people, and then you plan your crimes, and no one would ever expect you that you're going to do it at church. And so great place to do that. So that's why there's more crimes where there's more churches. Okay, doesn't make a lot of logic. But here's the thing, and again, this is the directionality problem, is that it's possible that crimes are actually causing churches. Maybe in cities where there's more crimes, it feels unsafe. And so people want answers for why life is so scary, and they want to feel safe and comfortable. And so that's why there's more churches in those cities. So what we're talking about here is that we could say churches cause crime, but also it's possible crimes cause churches. We call it the directionality problem because you don't know which direction the cause goes. Now, again, one makes a little bit more sense, but that still doesn't mean we know that to be the case. And then the third explanation is what we call the third variable problem. So we've got one explanation. A causes B. So churches cause crime. Directionality problem. Also, we have B causes A. Crimes cause churches. So those are two explanations. Third explanation is what we call the third variable problem. And that's where essentially the argument here is that churches and crimes are not related to each other directly. They are only related to each other through a third variable. And that is likely to be the the best explanation for what we're seeing here. All we're seeing, the reason why these two variables seem to be related is because what actually connects them is size of the city. So here's a very small city, has very few churches, has very low crime because there's not that many people living there. Here's a medium-sized city, or a slightly small to medium-sized city, has lowish levels of crime, lowish levels of churches, lowest crimes, lowest churches. Here's a larger city with more crime or with more churches, and so on. And so essentially, the only reason these two things are connected is this third variable, size of the city. So the most common example of the third variable is a third variable issue. In statistics is it's kind of overused, but it's I feel like I have to teach you this, is that it's the correlation between shark attacks and the amount of ice cream sold in New York City. Those are very strongly correlated to each other. But again, like, why do sharks care that people are eating an ice cream, or why do people want to eat more ice cream when people are getting attacked by sharks? No, they're not, because it's not causal. The reason they're related is temperature or season. When it's warmer, people are swimming more. As a result, they're more likely to get attacked by a shark or more available to the sharks. Likewise, when it's warmer, people like to eat ice cream more. When it's colder, they eat ice cream less. And so those two variables are not actually directly correlated to each other. Instead, they are only correlated through a third variable. So that's why we have to be so careful with interpreting correlations. So correlation does not mean causation. And the reason why is that it's only one of the possible explanations. There are multiple explanations. A causes B, causal, sure, but one variable causing the other. But also directionality problem, we have then it could be B causes A. So that's a second possible explanation. And then the third explanation is the third variable problem, where they're not actually related to each other. They're only related to each other through a third variable. So this is the kind of thing that you just have to kind of keep an eye out for. Now, and again, also you want to be keeping an eye out for, when I go back to this example here, chances are, I mean, and it's also possible here, we only have 10 cities. That we might be getting this strong positive correlation only by chance. If we sampled another 90 cities, maybe we get dots all over the place, and this would end up being a zero correlation. So it just happened to be the first 10 that we measured had this strong correlation, and that happened by sampling error. It's chance. All right, so that's also something that we have to keep an eye out for, and that's why, and that is essentially that issue versus statistical significance versus just a coincidence. It is possible we just happen to sample the 10 cities where there is this strong correlation. Okay, so hopefully that helps with that. And again, that is a very common thing. And so if you're ever interested, there's a lot of things online regarding this. One is called Spurious Correlations. Oops. And this is just where it will actually create things where it looks like these two variables are related. It has access to a bunch of data and just asks, and you can just actually, it's essentially using AI and an algorithm to go in and explore the data and just try to find things that look like they are connected. And so in this case, it's the annual household spending on alcoholic beverages and the number of septic tank servicers and sewer pipe cleaners in New Hampshire. Now notice how those all seem to kind of move in the same direction. That is some indication. It's not a correlation coefficient like we've been looking at, but these two variables seem to be correlated with each other, and it's just purely by chance. So there's a bunch of these. Kerosene used in Romania, and Google searches for why isn't 11 pronounced 1D1? Like, so there's just all sorts of things. So if you're interested and want a little bit more help with this, there's going to be a ton of information online in terms of this idea of correlation does not mean causation. Okay. And then the last thing here is the difference between correlation and regression. That's all I'm pulling out of this last one. And I would just simply say, don't worry about it. In this class, all we're going to do, and all we'll ask you to calculate, is the Pearson product moment correlation. So you're going to calculate your correlation coefficient, and that's it. But just so you know, because you will be consumers of research, is that regression and correlation are very, very similar. They basically measure the same thing. How are these two variables related to each other? The difference is that the regression gives you actually the line that best predicts the data, and it's called the regression line. So let me pull back up this website here. So we had our correlation of 0.70. That line right there is the regression line. So if I wanted to know, if I knew somebody scored, let's say, a 95 on X, what would I predict their Y is if these two variables are related at this point, positive 0.70 correlation? Well, once I establish this line here, the regression line, it has a formula, and those all lines have a formula where Y equals some slope times x plus a constant. So they just reversed it. So they do the constant here, 58, plus the slope is the 0.42 times x. So basically, if I knew I had an x of 95, then I would essentially then, oh, well, let me just do 100 because it'd be easy for the math. So if I knew somebody had an x of 100, just multiply 100 times 0.42. That would be 42. So 42 plus 58 is 100. So my prediction would be if that person had 100 on X, they would have 100 on Y. And that's exactly where that line is. So again, if I had an 85 on X, I could just go up to the line and say, oh, they'll probably have about a 94 on Y. And so on. And you just plug the number into the calculation. So what it's going to do is say, this is our best prediction. Now, one thing to know is that that's the advantage of the regression, is it just simply gives you that formula. We can calculate this formula from our correlation. The slides sort of show you how to do that, but we don't get into that. But that's just, this line is where some researchers kind of want to know things because they're trying to predict how well you're going to do in graduate school based on your GRE score or your LSAT or your MCAT. And so they might create a correlation. And here's what it would actually look like, just so you know. Most of those have correlation around a 0.3. So there's your correlation between your GRE score and your graduate college performance GPA. Again, somewhat related, but only 9% of your GPA in graduate school could be explained by knowing your GRE score. But if I had to know, I was like, well, that line is going to be the best prediction. So what you can see is that line's not going to do a great job of predicting most people because there's just so much difference than that line. And that's where the line gets more and more useful the stronger it is. So let's say we've got a really strong correlation of 0.94. Now, pretty much, I know what your X is. I'm going to be really close to knowing what your Y is likely to be. And that's really all that the regression part is. And so again, I'm not testing you on any of that, so you don't have to worry about knowing regression. But I just want you to be aware of it because you are going to see regressions in the literature. So essentially, when they're calculating, they're doing the same thing as a correlation coefficient. They're just trying to say, are these two variables related to each other? And then how strongly? And is it a positive or a negative relationship? Okay. So that's it for this chapter. Sorry for all the technical issues, but otherwise we've got one chapter left. We've got the chi-square. There's actually two versions of it, but it's kind of has the same formula either way, just sort of a slightly different setup. Okay, well, as always, let me know if you have any other questions. Otherwise, good luck. Got a little less than a week left.